Welcome to solverfy.
In this question, we will be using the lower flammable limit, which is usually given in volume percent, to look at the combustion of hexane. And I have our chemical reaction, our balanced chemical equation right here. And for the first part of this question, they are asking what the LFL is going to be for hexane when there is a certain percent of O2 in the air. So what we're first going to need is the density of hexane, so C6H14, and the density they give us is 0.66 grams per centimeter cubed. They tell us that the volume of air is equal to 1.000 meters cubed. And they also tell us that the volume of O2 in our air sample is 20.9%. And we know that the molar mass, or mm, of hexane is 86.175 grams per mole. Alright, so for our chemical or our balanced chemical equation, for constant temperature and volume, if these are proportional, then we know that the moles of our gas is proportional to the gas's volume. So as we can see in our balanced chemical equation, we have 19 moles of O2 and we have 2 moles of our hexane. So our 19 moles of O2, so we're going to say that that's our volume of O2, so that's there, and then we're going to say that that is proportional to 2 liters of our C6H14. So now to get our volume of hexane, we're going to take 1 liter of air. Since our air is 20.9% of O2, we have to take account for that. So we're going to times that by 20.9 liters of O2. Divide that by 100 to get the percent out, liters of air. And then we're going to times that by our ratio of O2 and hexane. So that's 2 liters of hexane divided by the 19 liters of O2. When we calculate this out, our volume of the hexane is 0.022 liters. So now let's get the percent of hexane that we have, or the volume percent of hexane that we have. So volume percent of hexane is equal to the volume that we just found, 0.022 liters. And then we're going to divide that by 1 liter of air and times that by 100 to get a percent. When we calculate this out, it's going to equal 2.2% hexane. So the lower flammable limit is usually half of the stoichiochemistry of our balanced equation. So we're going to divide this 2.2%, divide that by 2, so 1.1% CH6 of our hexane. So this is our lower limit, or our lower flammable limit of hexane. For part B of this question, it is wanting us to find the volume in milliliters required to produce a flammable mixture at standard temperature and pressure. So we're going to take our volume of hexane that we just found, so 1.1% hexane. And let's turn this into liters instead of a percent. So we're going to times this. So 0.0 times 1,000. And this is going to get us 11 liters of our hexane. Alright, it says that this is happening at standard temperature and pressure, so we know that our pressure is going to be 1.0 atmosphere, and our temperature is going to equal 273 Kelvin. Alright, so let's find the moles of our hexane that we have. So we're going to be using PV is equal to nRT. So we're going to solve for N, so PV over RT. So N is going to be equal to 1.0 atmospheres, times that by our 11 liters of our hexane. We're going to divide this. I'm going to be using the R value 0.0821 liters atmosphere per mole Kelvin. And then we're also going to times that by our 273 Kelvin. When we calculate this out, we're going to get 0.491 moles of our hexane. So now that we have the moles of hexane, we can now get the mass of hexane using its molar mass. So mass of our hexane is going to be our molar mass, so 68 or 86.175 grams per mole, and we're going to times that by our moles, so 0.491 moles. So our mass is going to be 42.31 grams of our hexane. So now that we have our mass of hexane, they did give us the density of hexane. So we're going to use our volume of hexane is equal to the mass over its density. So this is going to equal 42.31 grams over the density is 0.660 grams per centimeter cubed. So grams are going to cancel out, so this is going to be 64.11 centimeters cubed. So centimeters cubed is basically saying centimeters cubed. So 1 centimeter cube is equal to 1 milliliter. So our volume of hexane is equal to 64.11 milliliters. And that is the answer to part B.